Okay, so thank you to the organizers for the invitation. I mean, to accept me to give a talk here. And as you say, this is joint work with Cecilia that I saw that she's here. So hi, Cecilia. And I suppose Philippe is around. So hi, Philippe. And yeah, so yes, so I will talk about, as the title says, on fragmentation process that one can construct by, let's say, destroying these stable Galton-Watson trees. And in fact, the motivation of this work started by, we wanted to, in fact, study Bernoulli-Bon percolation on these alpha stable Galton-Watson trees and understand the sizes of the connected components. But then we noticed we could say it a little bit more on than just study the sizes in the like in a fits setting. Okay. So let me start by presenting the model. So I should say that my talk is a little bit informal, so I won't define precisely all the objects I will use, but I will try to more or less explain the main ideas, and hopefully I will arrive to the main results and you will be able to understand it. And well, if the time allows, I will talk about some ideas of the proof. So this, what I will talk about was, well, it comes from a series of papers from these authors you see on the screen, which is Aldous, Evans, and Pittman, who study the fragmentation process of uniform random trees on a set of n-labeled vertices, also known as Cayley tree. And they destroy this tree by deleting its edges one by one in a uniform random order. So let me be a little bit more precise and define this process. But I will make a modification. I will define it in continuous time. So the idea is as follows. So you consider any tree with n vertices, rooted tree, I will consider in this talk. And let's say you keep all the edges of this rooted tree by some uniform random weights on 0, 1. And then what you will do is that for every fits u, you will keep the edges on the tree which corresponding weight is less or equal to u and delete the others. So for example, here you have a small simulation. So what you do, let's say you delete some of the edges, which weight is bigger than u, and you create a forest, which is formed by some subtrees of the original tree. And you can see that, okay, we have the same number of vertices as in the original tree, just less edges. So the quantity of interest in this talk will be like for every fit u, we want to understand the evolution of this function on u, which will be given by the sequence of sizes, number of vertices, in this case, of the connected components of this, let's call it fragmentation forest at time 1 minus u. And I will rank it in decreasing order. So you see that the evolution of this process as u varies and in fact, as u increases to 1, you remove more and more edges on your tree. And this basically disconnect, every time you remove an edge, you decompose or split the corresponding connected component into 2 subtrees, right? So you see that as edges are removed, I have kind of a fragmentation phenomenon going on as I look to let's say, the sizes of the connected components. And in particular, with this parameterization is I put, let's say, u equals to 0, that means that I will keep all the edges. And well, I only have one connected component of size n. If I put u equals 1, that means that I already removed all the edges and I only have well, isolated vertices. So all components have size equals to 1. Okay. So what Aldous, Evans, and Pittman did was on the case when this discrete tree is a Cayley tree of size n, they try to understand the asymptotic behavior of this process. Okay, so let's see if I can. Yeah. Okay. So what they prove is the following result. So they showed that if you rescale properly the space and time of this process, the discrete fragmentation process, it converges, in fact, to another fragmentation process. And in fact, the fragmentation process you get at the limit is the fragmentation process of the so-called Brownian CRT. And is essentially defined in the same way as in the discrete setting. But before that, I would like to say that it's kind of natural to expect that you will get kind of a fragmentation of some tree on the limit, knowing the fact that it's well known that if you take a Cayley tree and you properly rescale the edge length by a factor of square root of n, 1 over square root of n, and you make the size goes to infinity, this converges to a limiting object, which in fact is a continuum tree, which we call the Brownian CRT. And the Brownian CRT, well, one way to represent it is as a metric measure space. It's as a metric space, which is rooted to distinguish one point, which will play as the role of the root of this continuum tree. And there is an additional measure you put on this space. It's in fact a probability measure, and this measure will is called the mass measure, and we will use it to measure the sizes of some subset of this tree. So how this fragmentation process is defined? So it's similar in that in the discrete. The only difference that we will consider now a Poisson point process of cut with intensity given by the Lebesgue measure, which will be kind of the represent the time evolution, times another measure which is known as the length measure. So this length measure is supported in what is called the skeleton of this Brownian CRT. And the skeleton of the Brownian CRT is, even though I won't define it formally, but you can think about as the edges of this continuum tree, right? And a way to think about this length measure, how to define it, basically is the kind of equivalent of the Lebesgue measure on this metric space. So it's the measure induced by this distance. Okay, so how it works? So just say you have here a silly picture of the Brownian CRT. And what you do, you let range Poissonian marks on the skeleton on the edges of this continuum random tree. Then you remove these marks, and what you have is a collection of smaller subtrees of the original one, as before. And then you look for every fixed time s, the sequence of sizes of, or in this case, the mu masses of these connected components at some time s, and you rank it in decreasing order. So here we use this mu, this mass measure, which comes with the continuum random tree to kind of define the sizes of the connected components, since we don't have, we cannot count vertices on the continuum. Okay, so this is the process we get at the limit for this discrete fragmentation. So some nice connection about this fragmentation process of the Brownian CRT is, in fact, that if you kind of do a time reversal, you go in the opposite direction on time. So instead of fragmenting or cutting down the tree, you kind of joined different connected components. So you have the opposite of fragmentation, which is coagulation. And in particular, this fragmentation of the Brownian CRT, you change it by you time change it by some exponential time change. You get the so-called standard additive coalescence. And this object, this standard additive coalescence, will appear as a limit of several other models. And in particular, there are some connections to parking schemes, and in particular, this cannot parking problems. And here, for example, I have seen that Svante is here, so he has done already some work on that. And other people too. Okay, so we have defined this fragmentation of the Brownian CRT. And as you can see, I call the Brownian CRT this continuum tree I got on the limit. And since it has the name Brownian on it, you might expect that, well, if you don't know, there's a Brownian motion which is behind this tree, right? So in fact, some people here probably know that another way to construct the Brownian CRT instead of consider a scaling limit of discrete trees is to define it as the tree which is encoded by an excursion type function. In this case, is the Brownian excursion, right? So a natural question is, okay, we know that we can construct this fragmentation of the Brownian CRT using a Brownian excursion. It is possible to define directly this fragmentation process using this excursion instead of cutting down the tree? And the answer is yes. This is a result due to Bertrand. He showed that this fragmentation associated to the Brownian CRT can also be constructed via the Brownian excursion, which encode the Brownian CRT. And here I will roughly recall how to do it. Using the Brownian excursion. So essentially, you consider your Brownian excursion. What is the Brownian excursion? you take essentially Brownian motion on the interval 0, 1. You condition the Brownian motion to be positive and to start at 0 at time 0 and to finish at 0 at time 1. Okay, and this is a silly simulation done by me of the Brownian excursion. Okay, so how you define a fragmentation process using this excursion? Well, you define this process that I call YTS, which is just the Brownian excursion minus a negative drift, linear drift. And then you consider this process I, which is just the current infimum of the process Y. Then you define what is called the ladder time set, which are all the points where this process Y coincides with the infimum. Okay. So for every fixed time t, you have a collection of points. So what you do is you take your interval 0, 1, you remove this collection of points given by the ladder time set, and you essentially end up with some open subinterval of the original interval 0, 1. And then the definition of this fragmentation process at time t using the excursion is just the length of these open intervals arranged in decreasing order. And it's not difficult to see that there is some kind of monotonicity due to the way I define this process, this Brownian excursion with drift. And one can show that in fact this ladder time set is an increasing set in t. So that means that as t increases, you add more and more points at the ladder time set, meaning that the partition of your unit interval will become finer and finer, and you have a smaller interval, and therefore they will have smaller sizes. And again, you have a kind of a fragmentation behavior. And in fact, one can precisely characterize the law of this fragmentation process, and it belongs to a very important family of fragmentation process called cell-similar fragmentation process, which again is the name cell-similar comes because, as you probably know, the Brownian motion has a cell-similarity property, and it's kind of this fragmentation process is also have this kind of similarity property. Okay, so this is what is known about this model. So what is our framework on this work with Cecilia? We wanted to extend this result, and a natural extension will be, instead of cutting down only a Kelly tree, why not to cut down a Galton-Watson tree conditioned to have size n. And in particular, we consider that the offspring distribution, which I denote by nu, is critical, and it belongs to the domain of attraction of a stable law of index alpha between 1 and 2. For example, you can assume that this offspring distribution has this state behavior. And from now on, I will refer as Tn as the alpha stable Galton-Watson tree. So as for the Kelly tree, which is, as I said before, if you rescale it properly, this will converge to the Brownian CRT. So for this alpha stable Galton-Watson tree, you have a similar result. So there sits a sequence, which I will denote by Bn, so that if you rescale properly the edge length of this discrete tree by a factor Bn over n, and you make the size goes to infinity, you will converge to some limiting object. In fact, this limiting object is another continuum random tree. This is called the alpha stable Levy tree. And in particular, when alpha is equal to 2, you recover again the Brownian CRT. So here, well, I have the formal statement of this convergence, so but don't worry about that. So just recall that there is a sequence which we use in the scaling. This sequence will appear later. So something about this sequence is that well, this sequence Bn I use one using the result of the scaling limit of this stable Galton-Watson tree, that if you divide it by n to the power 1 over alpha, is a slowly varying sequence. And in particular, just to justify that this is a generalization of previous result, that the Kelly tree is a particular case of a conditioned Galton-Watson tree when you consider that the offspring distribution is given by a Poisson law of parameter 1. And in this case, this sequence Bn we use on the rescaling is given by the square root of n. Okay, so this is the framework we consider on this work. And what is the main result? What we prove? So again, just recall that we consider now a Tn alpha stable Galton-Watson tree. We keep the edges of this tree by some uniform weights on 0, 1. And we let Fn of u be the forest obtained by keeping only the edges on the tree, which corresponding weight is less or equals to 1 minus u. And we define this process that now I led to define of the index alpha Fn of u with the sequence of sizes of the connected components of this, let's call it fragmentation forest at time 1 minus u, and I rank the sizes in decreasing order. So what we show first is that if we consider the sequence Bn appears on the scaling limits result for these guys, and we properly rescale the discrete fragmentation process associated to the alpha stable Galton-Watson tree in space and time, then we converge to another fragmentation process, and this is the fragmentation process associated now to, let's the normalized excursion of a stable spectrally positive Levy process of index alpha between 1 and 2. So in particular, when alpha is equal to 2, this stable excursion is the Brownian excursion. And how this fragmentation process associated to the stable excursion is constructed is exactly defined in the same way as in the Brownian case. The only difference in my definition, you change the Brownian excursion by now the stable excursion, and it's exactly the same construction. And the second main result we prove is in fact that this fragmentation process associated to the stable excursion can be also constructed or equal in distribution to the fragmentation process you can construct by cutting down the alpha stable Levy tree, which is kind of something that one might expect to obtain. And well, essentially, these two results kind of generalize all these previous results of Aldous, Evans, and Pittman, and the result of Bertrand. Something that I didn't say, and I haven't explained why I consider this scaling, this time scaling on the limiting theorem, even for the Kelly tree case. The factor 1 over n in the scaling of the space is just because, well, recall that f of n is just keeping the information about the sizes. If I divide by y over n, basically I'm saying is I sum all the sizes of all connected components and divided by n, the size always constant equals. I mean, the mass always equals to 1. So in a moment, I will explain why this is, well, kind of the right time window you need to consider if you want to kind of observe something not trivial on the limit. Okay, so this will come on the next slide. So maybe some comments. Well, one first comment is that, in fact, at the same time we were finishing these works, another paper appears related to this topic, and it's a paper due to Paul Seveny, who is now a postdoc in Uppsala. And he proved that there is another way to construct this fragmentation process associated to the alpha stable Levy tree by consider kind of a geometric approach, and is constructed in terms of another nice object called laminations. So he defined a kind of a nice lamination value process, and that is encode this fragmentation process of the stable Levy tree in a very nice, clever way. But I won't talk about that. So I just wanted to point out this another connection of this model with another object. And my other comment is related to the connection with Bernoulli bond percolation, which motivated this work on this alpha stable Levy tree. So what is the connection? So recall that we keep edges with some uniform weights on 0, 1. So what is the probability that an edge on the tree has not yet been removed at some time u? Well, it's the probability that the corresponding weight is less or equals to u, which is the probability of keeping this edge. And this is equals to u because the weights are uniform. So in particular, the configuration of the connected components of the forest, the specific time window I'm considering, is that that one can observe one perform Bernoulli bond percolation on the alpha stable Galton-Watson tree with this parameter 1 minus Bn over n at time t for some fixed time. So for some result of Bertrand, one can see that this is exactly correspond to the supercritical regime on percolation, in the sense that if you perform percolation with this parameter, you know that you will have one giant component. And this kind of result kind of justify that this is the kind of right time window you need to consider if you want to somehow get something not trivial on the limit, because you know that there is something that is of order n, right? Okay, so let me move on to some of the idea of the proof. So I will talk about just the main idea of the proof of theorem 1. And to prove this, we use something that comes from computer science. This is called the prim algorithm, which we discovered when we were working on this problem. And we use this procedure to explore the connected components of the fragmentation forest in a very nice way. I will explain in a moment. And this prim algorithm is also known because you can use it to obtain the minimum weighted spanning tree of a graph. And in this case, since our graph is a tree, it behaves very nicely and we have nice properties. And in fact, this way to use the prim algorithm to answer this type of questions was already studied by Bruton and Market in another paper. And somehow they use this procedure to give another proof of the result of Aldous, Evans, and Pitman in the Cayley tree case. So here we kind of use some of the ideas, but we cannot exactly use the same approach because they rely on some nice properties of the Cayley tree, which only hold for this type of tree. And alpha stable Galton-Watson tree are usually more technically challenging. And also we have to modify slightly the exploration process they use on the paper. And this is what I will try to explain in what is left of my time. Okay, so what is this prim algorithm, or how can we use it to study this fragmentation process? So again, you consider Tn via alpha stable Galton-Watson tree, or you can consider any tree, discrete tree you want. This will work the same way. And you equip the edges of this tree with some uniform weights, right, as this picture. So how it works? So if this prim algorithm, we will use it to kind of give an order of exploration of the vertices of this tree, or some labeling. So you start by exploring your tree from the root. So this will be the first vertex according to this prim algorithm. And then you look to all the neighbors of your root. And then you choose as a next vertex on this procedure as the neighbor which corresponding edge has the smallest weight. So in this example, you have 3 neighbors, and the smallest, the edge with the smallest weight, it corresponds to this left child, which has weight 0.12. And this will be the second vertex you will explore on this procedure. Then what you do is to now look to all the neighbors of these 2 vertices that you have already explored. And again, you choose a neighbor which corresponding edge has the smallest weight. In this case, is this one which weight 0.2. This will be the next vertex you explore. And you continue in the same way, always kind of choosing the neighbor which corresponding edge, connecting edge has the smallest weight. And this gives you an order of exploration that we call the prim order of the tree, or the vertices of the tree. So, but we are not interested on the exploration of the tree. We are interested in exploration of the fragmentation forest as some fixed time U, right? Which is again created by just keeping the edges which corresponding weight are smaller than U. So here you have again, well, I will explain this with a picture. So let's consider U equals to 0.60 on the previous example. So that means that you remove 2 edges which weight are bigger than 0.60. And how this prim algorithm work on the forest? Well, again, you start from the root. Then you look to all the neighbors of the root on these connected components. And again, you choose the neighbor which corresponding edge has the smallest weight. In this case, it's this one. And now, again, you have explored 2 vertices. You look to all the neighbors of these 2 vertices, and then you choose the one which corresponding connecting edge has the smallest weight. In this case, there is only one option. You go to this one. When you finish to explore a connected component, what you do is to choose the next vertex according to that you have not explored before, according to the original prim order on the tree. So since you have explored these 3 vertices, the next one according to the original prim order will be this one, which is the isolated one, right? 3. And you move to this one. And again, you kind of, I guess you understand the idea. You move to the next one, and then you always go to the neighbor which edge has the smallest weight. And then you will say, Gabriel, you just wasted time because basically what you did is just to give the same order as you did for the original tree, without removing any edges. And yes, this is what I did. And this is what is nice about this prim order, or this prim procedure, that the exploration of the original tree or the fragmentation forest at every fixed time U is always the same. It doesn't change. So you have a kind of consistent way to explore your fragmentation forest at any time. But we are not interested on the order of exploration. We want to use this order of exploration to define an object that gives me some information about the sizes of the connected components in a consistent way, that for every time I have information about the sizes of the connected components. And the way to do that is to define a random walk as follows. So again, you fit some time u on 0, 1, you consider a vertex on the forest at time u, and you define C of ub be the number of children of this vertex on the forest at time u. And you define a random walk as follows. It's a random walk that starts at 0, and which k increment is given by the number of children of the k vertex according to the prime order at time in the forest at time u minus 1. Okay, and we call this random walk, which depends on u, the prime path. And maybe with a picture it's easier to understand how this thing is defined. So again, it's a random walk. Let's consider the previous example as before. And it's a random walk that starts at 0. And then the next step will be given by the number of children of the first vertex according to the prime order minus 1. So in this case, the first vertex is the root, it has 2 children, minus 1, 1. So that means that the random walk will make a step of size 1. Then you move the next step of this random walk will be given by the number of children of the next vertex according to the prime order. In this case, it's this one, we label 1, which has 0 children. Minus 1, that means you get minus 1. So that means that the random walk will give a step of size minus 1, and so on and so forth. Right? Okay, so people here might recognize that this is very close to another random walk you can define associated to this type of forest, which is the Lukasiewicz path. And it's defined exactly the same way. The only difference that instead of consider the prime order on the vertices, you consider the lexicographical order of the first search order of the vertices. The difference is that this exploration is not consistent in U. So every time you remove an edge and you do this exploration using the lexicographical order, the order of the vertices of the labeling might change. And something that doesn't happen with the prime exploration. Okay, but in fact, one can check, it's not too difficult to check that the Lukasiewicz path and the prime path, in fact, for every fit U has the same distribution, even though they are different. So why this random walk is the object somehow we need? Because in fact, it encodes information about the sizes of the connected components. So one can check that the distances between successive new minimum of this random walk correspond to the successive sizes of the connected components of the forest at any time. So for example, in this case, in this picture, so you start at 0, so the new minimum happens at minus 1, so which is a distance 3 from the previous one, which is 0. And it's precisely the size of the first connected component you explore. The next new minimum occurred at minus 2, and that means that it's a distance 1 from the previous one, and it's exactly the size of this isolated vertex, which is the next one connected component. So you can see that this random walk encodes the information we want. And what is left is to understand the asymptotic behavior of this random walk. For as let's say the time of the exploration of the forest varied, and also at the time U, which corresponds to this cutting down procedure, also varies. Okay, so to understand quickly, to study this the asymptotic behavior of this random walk, first you need to know what are the distribution of the steps of the random walk. But it's not difficult to see that it's just a thinning of the number of children on the original tree. So essentially, the step, as I say, is given by this number of children of the k vertex on the prime order at time u. And this is just a binomial random variable with parameter n given by the number of children in the original tree without removing any edge. And probability p equals to u, which is the probability of keeping these children, of keeping the edge which connect to your child, which is u because the probability of keeping an edge is given by the probability that the weight is less or equal to u. Okay, And again, since the prenorder does not change as U changes, one can in fact couple this process for several U's in a very nice way. And then you have a bivariate random walk, which encode all the information we need about these sizes of the connected components on this fragmentation process. So what is left to do is just to study this random walk on the right time window, which is when U is equal to this 1 minus Bn, which is the supercritical region in percolation. So again, part of the proof, well, is to check that if we consider the sequence Bn, which is the same as appeared in the rescaling limit result for the trees, and one rescale properly this random walk, it converges in distribution to the right object. And what is the right object? Well, it's just the process, what I denote by Y, which is just the stable excursion minus this negative drift, linear drift, which is you recognize from the construction used in the Brownian case, which is exactly the same process Bertrand uses to construct the Brownian fragmentation associated to the excursion. Okay, so this is very nice because we get this exactly what we want on the limit. And then what is left is just to use this result to subtract the sizes of the connected components, which is just by the property I showed you before. This is just one just need to study this the distances between successive new minima of both processes and see that they converge, which is it's technical, but it's not too difficult when you have the convergence of the random walk. Okay, so I will stop here and thank you very much. So I'm happy to take questions.
Thank you, Gabriel. Any questions? Are there any online questions? Okay, there seem to be no more questions, so we thank all the speakers of the session.